this edge was pretty prominent here, so this line has shown up. So, if your edge image is good, then it is, you can expect that you will get more lines or the lines in the correct way. Okay? And some other places where you can use that have like that the finding line or circles or comes kind of something like this. If this is the bowling, anyone of you have tried bowling? This is not cricket bowling, but bowling. So, here it is detecting the ball. How? By looking for the circle. Here is another example. Three coins are kept on a court and it is finding the coins. And this is something actually the next, I should not use that keyword project here because those are more like the assignment. So, the next assignment you will do actually this half transform. Again I will give you some piece of code, you need to write very short algorithm for the half transform. The algorithm is very straightforward for finding lines and for finding circles. Okay, so all this is everything whatever is done here is like finding the circle. Yes. Half is the name of the person. That guy came up with the algorithm, half transform. No meaning otherwise, okay? Okay. So, not only that, not only finding some lines or the circles, also you can, using the same idea, using this fitting idea, you can actually eventually, you can find out objects like cars. If you know how does a car look like, you can find the car in an image. Algorithm wise, that would be very much the same. So, now this fitting, how can you do the fitting? So, this fitting can be done by a parametric model. So, you are just fitting some parameters, for a line you have an equation, for circles you have an equation, for any other objects, we will see later that you can represent an object by some vectors of the edges. So, from that those are the parametrics model, and once you get the parametrics model, you just try to find those parametric model like those things presence in the image. Okay. So, what is the basic idea of the fitting? So, choose a parametric model to represent a set of features, and now once you get a member of that model, you may not tell that point belongs to a model. Example, if I just give you one point, you may not tell that okay, this point belongs to a line. So, the membership criteria is not local. If I give you 2 points, you can tell okay, they belongs to a particular line, but if I give you only 1 point, you cannot tell okay, this belongs to a particular line. Make sense? If I give you 2 points, you get that how many lines can go through the 2 points? If I give you 2 points, how many circles can go through that line? Infinite, because the radius may vary, right? But if I give you 1 point, you cannot talk about, neither you can talk about the line or the circle. Okay. Computational complexity is important because sometimes you cannot try all the parameters. If you remember a little bit from the yesterday's class, so for example, what is the example? The example was we are using some sort of grid, because otherwise my slope could be infinite. The theta can be minus pi to pi or 0 to pi, right, 0 to pi, but it is covering so many things. So many things means okay, you want to make 1 degrees increment or even less or even more, whatever the way you are doing. Okay. So, computational complexity is very important, and based on that you need to decide how coarse each parameters value you are looking for, and secondary thing, that how many parameters you are trying to fit, only 1, 2 or many. Okay. So, for circle we will see that if you are trying to fit a circle with a known radius, that is a simpler problem, but if I ask you to fit a circle with any unknown radius, the problem becomes harder. Known radius. So if I give you 2 points and if I give you known radius, how many circles can go through that 2 points? Only one. Two, right? Actually 2, because if this side and that side, so 2, but at max 2. If it is on that, what is that called? It is if it is on the that side, not vertical. The back, huh? Yes, yes, yeah. Okay, so that's the idea. Let's continue then. Then we'll talk about first line fitting and then the fitting circle and then some any other model. Okay, so let's go for the line fitting part. So while line fitting can be important, so sometime you want to find out the kind of the elevation of the building. Okay, and sometime you may look for the lane detection, which is a very common thing again. Autonomous cars, they need to detect the lanes, right? So that means they need to kind of detect the line. So your algorithm should detect the line. So there half transform can be useful. In the right now in the cricket matches you have seen that they find some lines. There also it can be useful, and in American football there also on that field they will have some line. There also it can be useful. So many places this algorithm can be used. Football also it can be used to find out that okay, if the ball is outside the court or not, right? Or if it is really a goal. The ball has passed across the line or not, goal post line. Okay. So lines are important. Now if you have the lines, how can you identify them? Now the question is, can we then just identify the lines just by finding the edges? Remember we have run the edge detection on, or shown at least the example of the edge detection on this image. So if I do the edge detection, cannot I just find the line? Can I? Edge detection does not give me a line, it just gives me some dot, and again there could be noises, so the lines may not be straight, and again it is not a parametric model. I am not giving any equation, I am just giving some pixels, I am telling that edges are there, and there will be many extra points, those are not lines. So no, so just from the edges I cannot find the line. Okay. So many problems extra edge points, so I do not want to worry about all those things. So there it is kind of the cluttered. There might be some circular parts, some straight lines, many other steps. So that is a big problem. And even the next problem is, even if I get something like this, it is a zoomed in version of this one. Again, see this line is not straight, this is coming here and here. So how to exactly find the line and which points goes for that line? How many lines I have? I should actually get 1 line and 2 lines here ideally. Okay. And another problem is of course like okay, sometimes the lines might be missing. So there no line is coming, but if I now have to find a line, the line should go perpendicularly from there to here because the lines equations goes infinitely. Of course you can limit it if you know the measurement. The drawing part you can limit, but the equation of the line doesn't limit, right? It goes infinitely. Okay. So all those issues you can, so and the noise measured in that, noise is actually very big, causes a big trouble. Now how the noises, how can you get rid of the noises? If you have some noises like as I am showing in this example, because there are some noises here, so these are actually kind of the noises in the edge image itself, and sometimes because of the noise you may not get the line by itself. So how to get rid of that? The main idea of that is the voting. So voting idea, the noises, started talking about the voting. If you have a straight line, all the points give some vote, right? Remember? And there would be a majority. If there are some noises here and there, now they will also give some vote, but the vote would be scattered. So the majority would be still the majority. I will talk about that idea again very clearly today and with more examples, more slides. Shonak? right? So, if noises, for the noises also we get some vote. If I take the theta and rho and theta is 180, how many vote I get for per point? 180. So, noise also gives 180 vote, but each noise is different, the direction will be different. So, their vote will be scattered. So, but so eventually they won't matter. That is actually the expectation. Okay. So that's why voting is useful, and we let the voting to go through that. We let the features vote, so like each point in the image vote for all the models that are compatible with it. All the models, very important, for all the rho and for all the theta, the way I was shown. Cycle through the features, cast votes for model parameters, look for model parameters that receive a lot of votes. That is the algorithm. Majority voting. Majority voting is very important idea, and it will come many times. Again later, whenever you are putting two images together, you will see the same idea of the voting will come up. Ransack. Okay. Model parameters means for rho and theta I am talking about. So everyone is giving for, okay, I want these two and this theta, this point is telling I want these two and this theta. So those are the votes. For circle you need how many things, how many parameters? How many? Location of the center, right, and radius. So three things. So those are the model parameters. Okay. So noises and clutter will also give vote, but as we are telling about that, their vote won't be centralized to any area. So it will be kind of the noise. So they will all will give in diverse way, the votes will get cancelled. Right? As I am telling yesterday, if you are a rebel and you just give vote to some random candidate, you can be pretty rest assured that the candidate is not going to win. Okay, that's the same idea. Okay. Now, whenever we are fitting the lines, some questions that you can ask are, given points that belong to a line, what is the line? Found the line, now we have to tell, okay, what line is that? Parametric equation. Two equations we can do, polar coordinate or Cartesian coordinate. How many lines are there? Is there only one line or multiple lines? There actually you need to make a decision. You need to definitely take a decision there. How many lines you are looking for? It is kind of the maximum number of words you are counting. Eventually you will get many. If it is a grid structure you need to assume, then are you looking for only the maximum one or many other? Like if you want to get 3 lines, then you need to take the 3 most important points. Okay? 3 candidates you need to pick. Which points belong to which lines? So actually one point can belong to multiple lines, that is possible. But based on the other points, I am just going to find some line. So for finding all those things, half transform would be used, and how does half transform work? The idea here is each point is going to give its vote for whatever all the compatible lines, and then I am going to get the one with the most vote. Okay. But the example will make it clear. So first, instead of going to the polar coordinate, let us talk about the Cartesian coordinate. So a very important, very fun thing. So yesterday I was talking about the duality, point line duality. Point line duality is a very important concept in this computer vision course by default. Whenever we will talk about the 3 division, you will again see the point line duality will come. Point line duality, this word may sound very technical. It is like one point can be represented as a dot. One point can be represented as a line in some domain. A line can be represented in a dot as in another domain. That is the idea, and we will see the very first example of that. So I have a line here, y is equal to mx plus v. Okay. And now if I have another half space, and in the half space I don't have x and y coordinate, rather I have the m and b. Then this line can be represented by what? A point of x coordinate, if the x is m, m0, and y coordinate b0. So, like this. So, a line becomes a point.
So we are just looking at the projection of the line in that gate, in that M.
You can tell it in this way. If you know projection already, then yes, you can always can talk about that. Okay, you are just changing the axis. Okay, so the main thing is, okay, this line is becoming only a point. Okay. Now, so if I give you a set of points x, y, I am just going to find all the m b such that y is equal to m x plus b. This is the idea. Now, given a set of points x, y, find all m b. Okay, all m and b. For one point, I am going to find all the m and b. That satisfies this. So, how many of those can be possible? For given set of points x and y, they are not in a line, right? So, you need to think about that one x and y, set of points x and y, find all m b that such that y is equal to m x plus b. So, this equation, if you have to satisfy by only one point, a set of points is written, that means one you try with one point, next with another point. So, if for every point you are going to get one line, for one point you are getting only one line, many lines, right, many lines. So, we will show you the example once again, then that would make you, that would be very clear to you. So, for one point you are getting many lines, but now if you have a set of points, each of them is going to give the votes, and if you get a majority you are going to pick that one. So, let us see. Now, we will just flip this whole thing. Okay. Now in the other way around. Okay. So, this is duality. Duality from means, okay, it will show go in both direction. A line becoming a point here, but now if I give you a point here, what is it going to be? That means it is going to be a line, because the line. So, if I have this point, solution is, okay, this belongs to a line and the solution is this, and this is a line of space for a fixed x naught and y naught, correct. Right. You will set a, right, exactly. Right, because of this equation. How are you getting this equation? From this equation itself, right? This is the equation. So, if x0 and y0 is known and you are looking for m0 and b0, how will you go for that? This is the equation. Okay? If you are looking for m and b, for a fixed point, if you want to know the m and b, this is the way of going. Clear? And this is the equation of a line. Okay? Clear? So, in this it is going to be a line. A point is becoming a line. Clear? This part should be very clear. Okay? Good. Now, if you get this part, most of the thing is done. And then, if I give you 2 points, what is going to happen? There will be 2 lines, and will there be an intersection? There should be an intersection, because if I have 2 lines, that means that both the lines can, there is a one line that goes through both the points, right? And a line can be represented by a point. and that is going to be the intersection of these two things. Make sense? So, one point can be represented by one line, another point would be represented by another line. That part is clear? And now, but there is a one line here that is going through these 2 points, right? And that line would be represented by what? A dot. That means there is a dot that represents this line, and why that dot should be? That a dot which is common to the line represented by these two. So, the intersection. Okay? Yes. The intersection, the whatever that intersection you are getting, this point, whatever m and b value you are going to get, that is actually the equation of that line. Is not it neat? Very neat, right? So, that is the idea of the half transform. Okay? So, from 2 points itself I can get. Now, what do you have to do? If you have 3 points, then the same thing would happen. If the 3 points are lying on the same line, then this would happen. If this point is here, of course, the intersection will be different. Does that make sense? If these 3 lines are collinear, so that is why they are going to intersect into a single point, because for that line there will be one point. Okay? Good, very good. So, now if I have like this, then it is going to intersect like that. Now, how can you find the exact value of this m0 and y0? The easiest way of doing it is having a grid value, because you need to calculate, like for each point you are going to, each point is going to give vote, idea of the voting, because you cannot try for all the m and all the m and all the b. So, you need to find out, okay, if the kind of a for loop for m is equal to this. Okay? The m values and b values. Yes. Otherwise, how will you do? Because why cannot you? The m cannot go. M can go to m slope. Yes. 0 to 1. And other side it can slope can be also negative. Minus infinity to infinity, right? So, it can go to infinity. So, that is the problem, right? So, as it can go to the infinity, so actually this approach does not work, and that is why actually that is the reason for going to the polar coordinate system. Okay, so we are going there. So, that is actually the problem. That is why m and this idea is not usually used. We will go to the polar coordinate, because there it is limited. Okay, as it can go from the infinity, that means I cannot have infinite grid, and I do not know how to discretize it. So, though this approach looks fine, but it in real life it does not work. And also, if it is infinity, then for a vertical line I am not going to get any slope, right. So, those problems would come if I have a really vertical line. No slope, I am not going to get any slope there. So, those problems would come, but right now otherwise the idea is clear. You are having some
This is not the part of the Howrah algorithm.
this.
Howrah algorithm, this is not the part of.
So, we will go there. So, half transform is telling that, okay, you can have the m, it can be positive and negative. So, if it is positive and negative, you need to have 2 different of those things, and again vertical lines, you cannot find those vertical lines from this algorithm. So, all those problems will come in. Okay. Then you won't get the m, no, the m itself is vertical. So, what is the m value of the m? So, you are not having the m itself. Okay. So, that is the idea. So, actually this idea won't be used. So, but the idea is clear that how you can do that. Now, the problem will come, and that is why I will not use this idea, but rather will go to the polar coordinate. Accumulate votes in discrete set of bins, parameters with the most votes indicate line in the image, right. Now the problem of this is this, with the usual MP parameter space, it can take infinite values undefined for vertical lines. So I really cannot do much. Okay? So I need to move to polar representation. What is the polar representation? The same idea, this time instead of the m and b, I am going to go for the theta and the distance. So x cos theta minus y sin theta is equal to d. So again I am just telling you that this theta is negative, but if you just assume this theta is positive, it is based on the representation, the equation will be plus. Okay. So this is how to, this is the equation of the line. For this line, this is the equation. Okay. So now a point in image space becomes a sinusoid segment in half space from this equation. Half space means the other space we are talking, that m and b last time I had, this time the half space is theta and d. That is the half space. So whenever you have to write the half transform algorithm for line detection, you are not going to do the m and b zone, that is just shown you just to appreciate how to do that idea, but you should do the polar coordinate style. What is the algorithm? You need to create a half space or half grid like this, d and theta, initial is d theta is equal to 0, d will go from a particular range and theta will also go from a particular range, and then you will just keep on giving vote for each edge point. So your starting point is the edges, from the image you get the edge, and from the edge you just start for each edge point you are going to give vote. You do not do the half transform on the whole real image, because why? Because there will be so many points. Edge image would be edge points are a limited set of that whole image, right? So you will go for the edge image for each edge points I x y in the image. All you are going to do is you are going to limit your theta min to max. Theta min and theta max, or it can be 0 to 180 degree. Okay. This is the equation. This is the equation of the line. Which one? Is equal to 0. That means you have a big matrix, that is there you are putting 0. That means no vote. This is used for voting. So no one has given any vote yet. Whole matrix. And then for each of these you are just going to calculate that, because you already have the x and y, you for each theta you are calculating the d and you are updating this. After that, when all the points are done, you find the value where this is maximum. You may find only one point, you may find multiple point, every point is giving you one line. It depends on how many lines you want, based on that many maximum values you need to take. Okay? And then detected line, so you got the d and theta, from the d and theta you can just now draw the line, this is the line, like a line equation. Okay? Now what is the time complexity? Time complexity, all of you know, BDA, you learned it. So what is the time complexity of this process? How many votes? D theta votes. Really? Huh. How many votes? Okay, how many voter? How many voter? How many? But how many voters? More XY, what to get from the XY? You like XY very much. Every edge points, right? Every edge point. So those are the voters. So how that many edge points, that many voters, multiplied by that many theta, that quantization you are taking. So you can just tell that multiplied by that, which is actually constant because all these things are known. So time complexity you can tell constant in terms of number of voting elements, that is edge points. Okay, and the space complexity. Now space complexity is actually causing the problem. Space complexity is how big your matrix need to be. How big in your matrix need to be? Your matrix will be to the power n because that many votes you need to store. N here is 2 for 2 dimensional because you are looking for only 2 parameters, d and theta. Okay, now actually I will show you some fun algorithm, and that there you can actually really appreciate. I am telling that each point becomes a sinusoid. Each point in the image becomes a sinusoid in the half space. If the half space is consisting of dimension is you need to quantization, you know, remember? You know a range 0 to 180, you know the range. Now you have to quantify like how thick you want to make. 5 degree, if it is 5 degree, then in the x coordinate how many you will get? 180 by 5. If it is 1 degree, you will get less. If it is 0.5 degree, you will get more. That is the grid size in the 1x dimension. The other side also the same. You will probably go from -5 to 5. You need to go minus side also for the D.
So if we just decrease the value of theta, so if we just decrease the value of gain, we will get the most prominent lines. No, it's less prominent lines.
Which one?
If we just decrease the value of gains, then we will get the less prominent lines. And
if you see, your accuracy will be less. If the number of beans are less, then what would happen? The line, wherever really the line, you will not find there. If the number of beans are more, then what is the problem?
even a minor line will be detected.
Not really. The other problem actually is you have a very prominent line, but because of the error, the same line has been taken by 2 beans. So your vote got reduced. Like if a party breaks, what happens? The vote divides. So some other non-minor line can be then the majority. That is one issue, that disk is always there, and you are may not find the 2 prominent line. And another problem is you may find double line. Though there is only a single line, you may find double line.
So we will select the threshold for selecting the coordinates and
Threshold means what if I threshold?
then there will be many lines for every element in the matrix. So we need a threshold or something to get the only prominent lines.
So that is the maximum value, that how many maximum value you want to get from the matrix, that is the thing you need to do. Okay. And sometime also we do non-maximum suppression, the same idea. In the grid, if you find that there are 2 points which are very close, you just take only 1 point, you don't take from the other point. Those idea also you incorporate. So non-maximum suppression is again one thing that you can use probably in many places in the computer vision. It will come again and again. You found a point which is prominent here, don't take the next immediate values, because those values would be like you found you probably guess that okay, just a table, right? You have a table in the real image. So you found one line here, because the table is have thick edges, then you will probably find another line which is like this, another line which is like this, right? But now, because why you are getting that? Because all the M and B or the theta or D are very close. Then you can tell that okay, if I have found one theta and D, I am not going to include or take the neighboring theta and D, because the neighboring theta and D is going to give me a line very close to the earlier line. Make sense? So all those things also you can do. Clear? So, this is kind of the engineering part, how many beans you want, how fine you want the granularity, and that is actually the problem of the half space, half transform. Now, actually if you see the algorithm, now this video is very useful and the best to understand how this thing really works. So, let us play that. You can see the x and y is flipped here, so you are getting a little bit different view. Now, this is the important thing I want to show. The key mouse. So, the voting is going on, it is going from the left to right, and it found the edge points and it is taking the vote. And this rotation is kind of the angle, you are trying all the angles, the rotation, the green things is rotating, right? That means you are just giving a vote for each of the angles. All the thetas for each edge point. So, that is the, and for each edge points you are getting a point there for that particular m is going left to right, and theta and the d is up and down or whatever they are getting. So, how this whole graph, the half transform image is getting generated, you are going to see from here. Okay, that's why this is the very important part, not the technical part, but this animation, how this graph, the half space graphs really gets produced. How does it look like? Okay. My mouse. What happened? It's coming good.
What is this block showing on here?
Let's see, huh?
This dot line,
That is the half space. That is the how the plot is looking like. Intensity plot. For every point you are getting some value, right? You are just putting a dot there. So dot means 1 vote. You are incrementing the color. It was at the beginning all black. What happened now? Just click there and play.
Theta and rho values and define exactly the occurrences of these points here.
So you are going left to right of the image, right?
This line occurs here and it founds a correspondence.
So the left side is getting updated.
Here it will sum in terms of this space here, and we can see that here we have 0 for all the values, minus theta for this side, plus theta for this side, minus rho for this side, and plus rho for this side. We can see that as long as the algorithm runs, it will discover different combinations
This is the matrix, but the image representation of the matrix, right?
of a line.
And everyone is getting a vote, so that is the votes getting increased, you are getting a whiter pixel. So now you can see that we are getting some intersection there itself.
Space and all the whitest points will define the detected lines in the input image. In the end of the Huff transform algorithm, we have to look in this image for the peaks, which according to this scale is defined by the whitest points. So here we have a peak, here another peak, here another peak. These peaks stands for the detected lines in the Huff
So in this image, usually how many peaks should I get? 4. So you can see that 4 dots are getting coming up.
detected here, and this peak stands for exactly this line here.
Definitely that point would be of this line. That's why it is coming a little bit slower. So yellow is this.
Possible to be detected in the C2 space, which is represented by 1, 2, 3, and now 4, the fourth peak in terms of detected points in the Huff space. And then it will go
Okay.
to the end of the
So this is the how the thing looks like. Okay.
well-known digital image processing book.
Now it is running. Wow.
Points here, and it founds a correspondence in terms of order.
So this point, what is the shape? This shape is an square because you can see the points. So these two lines are going to have the same what? Same theta. That means the angle. Okay. So now defined images. These images are not very good, of course. Actually, here it is coming good. If you see at home, it will come nicer, but it is not coming here.
that row, in the video we saw that the row was plus row and minus row. It was divided.
Yes, plus rho and minus rho. Yes. So minus rho would be some point, some lines are there. The like okay, if this image has a line here, line like that, the row would be where? Up, outside the image. So those are the minus thing. Distance, but distance kind of you need to treat it as a vector. So, if the distance is through that, if I have a line like that, the D is coming here positive. If the line is like that, the D is going to be in that way, negative direction. Okay. If I have a line like this again, right, like this, then what is the D going to be? The D would be like this, outside the image, negative. So, both the theta and D both can be negatives, because we need to consider the this what is it called, the consider them as vectors. Okay. So, in this image, if you see, this is the most prominent point, and probably which one, what do you think this point represents to? Most probably this line, I am just guessing, because this line is more prominent than others. And the edge image, how does the edge image looks like, that is another thing. Okay. So, if you have this original image, you can always detect the edge, but edge detection is very important here, because if your edge is good, then only the detection would be good. So, you need to play with the edge detection also, and once you get that one, for this, decode the vote of this, you are probably getting these 5 votes here. Now, the problem here is, you can see sometimes you can get votes which is very close. Why? Because probably there it may find multiple lines, right. So, probably this area, it is getting multiple votes here. So, those things, or this line, these two lines are very close. So, probably I do not know where exactly it got this one. You need to do the, you need to, once you plot this thing here, you know exactly what is happening. Okay. And so, that's how we do. Sometimes the points are very close, which is a bad, which could be a bad thing. So, non-maximum separation again may help at that time. You just keep only one line, you just get rid of the other lines. And this is some of the other examples, the real life example. This is the American football field. So, once you get the edge image, then you get the half transform, then you find the maximum lines, then this is the most prominent line that you are getting, the straight lines, and these are some other lines you are getting. Okay. And here, see, lines always go from the left to right, but here they just tried, based on the edge images, they just tried to limit the lines based on some sort of thresholding, but usually lines goes from the one side to the other. So, mainly we are showing the longest segments here. Okay. Very good until this point. Now, if you have noise is always a bad thing. Noise can cause you some trouble. Like you have really a nice straight line, but because you have noise, you have got the edge image like that, and then your votes are getting dispersed, not in a particular location, but it is, you are getting something like that. So, that means if you plot, then it is going to come many lines, close of almost of the same slope, but it would, there would be like line like that, right, because of this noise. So, noise is very bad, and if you have the noise, then all you need to do is first get rid of the noise. Noise, small noise won't cause you much trouble, but if the noise is huge, like if you have just some random number, you can still find some lines here, but literally there is no existence of line. Solution, get rid of the noise, of course, then try some of the blurring that we have learned and then apply. If there is little bit noise, the voting is not going to be impacted, but if the noise is very high, of course your result won't be that good. Make sense? Clear? Now, you study another idea we talked about, that from the 2-dimensional, can I move into the 1-dimensional space? How? Instead of the theta, this time some extension. So, this is the basic core algorithm I have shown you. Now, some extension. One extension can be, okay, I do not want to try all the theta, but rather for each edge points I want to get its gradient, that is the theta, and for that gradient I am just going to give a vote. So, this is the algorithm. What is the change here? I am not going over another loop for theta, but rather all I am going to do is I am getting the gradient. Once I get the gradient, I just calculate the d and give a vote. All the not gradient of all the thetas, all the points. Gradient all the points. So now that is how long will it take? Number of edges, very cheap. Right? Very cheap. Because for the edge image, anyway, you need to do that calculation. In the canny edge detector, how are you finding the direction, all those? You are anyway calculating those things, the gradient direction. Some other extensions can be used. Give more votes to the stronger edges. Direction and magnitude. So if the magnitude is high, let him give more vote, not only one vote but more vote. Okay? Some other extensions, change the sampling of degree of theta to give more or less resolution. We talked about that. That is totally on you. You have to see which one is giving you better result. Okay? Sampling. So theta 0.5 degree, 1 degree or 2 degree or 5 degree. How big we want to make the bin? The same way of the d. How big we want to keep the d? 1, 2, like how thick we want to keep the distances. Mainly how big you want the matrix. The bigger you make, the more computation, the more storage you required, the more computation you need to make.
If we make the interval larger, then in the edge image, if the edges are very closer, they will be considered as a single line.
Right. Now what do you want? That is the question. You may want a single line. So that is the thing. So it is totally, so it is an extension. It is totally depends on you, on your requirement. Okay. So these are, see, this is the basic algorithm and these are kind of the extension that you may need to adopt based on your need. You may want faster computation, so you do not want to go through all the theta, rather you want to get the image gradient and work on that. You may reduces degree of freedom, remember, and that means it actually boosts the space complexity a lot. You are reducing the dimension itself. Give more, and this is another way of giving, using the gradient, the magnitude of the gradient value. This is for you based on your own need. Extension 4 is that the same algorithm, the same basic idea of the voting with very little changes. You can use it for the circle, squares, or any other shape. So that is the next part. So OpenCV2 has something for the half lines. So you can just write CV2 half lines and it will give you the lines. But in your assignment 2, all you need to do is write this piece of code that works like half lines. You will get an image, you will just get the edge out of it and then run the algorithm. Okay. Using that. Again, so that later if you like, half lines will not do many things that you can do. You may give extra votes, the extensions that you can do. Half lines may not have those possibilities. So you can always do more stuff with your own code, and that would make your understanding better. How you will find some difficulty, you will find out that your theta values is wrong probably, and many things we will see that many things are happening. So your understanding would be stronger. Yeah. Otherwise, how will you find? Like each point, remember that one point cannot tell anything. One point cannot tell, okay, which line I belong to. But many points, if they agree, okay, we all belong to the same line, then you just pick that line. So that's why voting. Okay, so I'll give you 5 minutes break because line is over. Now we'll talk about the circle and other shapes. Just 5 minutes break. Just chill without making noise. Now just think, okay, if I have one point and I know these are the edge points, right? If I have the edge points, oh, they have changed this mic, I guess. Good. So if I have a one edge points and I know this edge point, now if I ask this edge point to give vote and the known R, what it is going to give the vote for? Hmm? L. We are not talking about the R plane at all because R is known. But R is known, so you can get rid of that. Okay, just think that you cannot, just you have to appreciate the idea that how this is a very fun idea, right? So I'm telling, okay, see, I have a hidden circle, but I am giving you only one point of the circle. I have to find the circle. I am telling you, okay, this is the point of the circle, and the radius is 5. Now, if you can give me some point where you can find the center, I am happy. Now, where that center would be? Where the center could be? Very good, 5 radius away. So that means you are actually going to give like vote like that. You don't know anything else, but you just know that. You are just giving vote, and the votes are, if you have the beans, that and the beans are only the A and B, so those coordinates are going to get filled. Clear? Right. Now, if you have many circles, they are going to intersect into a particular point, and that point is the center. So that idea is very important, that one point is giving vote as a circle, kind of it is telling, oh, it could be any side of this. So in half space A, B and B, for one point, this point I am getting a circle, this point I am getting a circle, for this point I am getting a circle, and there I am getting a intersection. Okay. Very cool idea. Where is exactly actually we need to do that. Okay. So, and remember we talked about another thing. If I just someone gives me 2 points, how many circles I can get? Like how 2 circles. So these are the other circle. This point. Okay. Clear? This center is not known. That is kind of the thing you are looking for. You just have the point, some points of the circle. Okay. So this is the idea. Now for unknown radius, how the half space would look like? Now you can think of, we were talking about the R is R, right? So R is included, not only A and B, but also R. How the shape would look like for one point? Sphere? Just think, if the radius increases, what happens? And that is what? How do the shape look like? If the radius is very small, almost 0, then the center and the point would be at the same location. Now radius gradually started, right? So what is happening? Nothing, a dot. Then little bit. This is the circle you are guessing. Along with that, you are increasing the R. So what is the shape looking like? Just increasing, not decreasing. Sphere for sphere, you need to decrease. From nothing to a big. Huh? It is a 3D shape, not 2D shape, right? 3D shape. So, a cone. Nothing, then gradually increasing, right? Just take a cone and just intersect that plane. You are getting a circle. R is increasing, you are getting a bigger circle. Okay?
We are basically increasing the radius, so it's going like
Right. Right. So, one point can give vote to so many things. So, this is going to be actually for every point you are going to get a cone. Okay? And in this way you will get many cones for many points, and then again actually eventually you are going to get some surface. There all the points satisfy because you don't know the R. So for so this is a harder problem by itself. You need to write. You need to give votes, and then you may get. And if the grid size is big, another problem is your voting element is less. That causes some more trouble. But the idea is, this is the idea. So okay, still they are going to give vote in this 3D dimension. Whoever gets the maximum vote is the winner. You get both the radius and the center and radius. That's all you need. Clear? A, B, R. These three parameters can represent any circle. So for unknown radius, for known gradient direction, here the advantage here is gradient direction is known. So you know that the radius could be only on this particular line, or not the radius. So the circle center would be only on this line because you know the gradient. Then every time you know the gradient one dimension, the problem becomes a little bit easier. You now know that the circle won't be here and here and here. It is a final fixed one direction. The center could be at any location, but it would be on this line because this is the direction of the gradient. In this way, for another line you will get for another point you will get another line, and this is the way you are going to, they are going to give vote, so you will get some majority somewhere. Clear, this part is clear?
and the point which all these lines intersect is the center. Point at which all these lines intersect.
Yes, is the center. Not in the center. So like still this is still a voting process. So you are giving a vote, whichever is getting the vote, that is the winner. The advantage here is you are giving less number of votes. Clear? Okay. Okay. So how does the algorithm look like? The algorithm looks like this. For circles, for each possible value, radius value r, provided the r is unknown, for each possible gradient direction theta, you calculate a and b. A is equal to x r cos theta and y is equal to y minus or plus, depending on the way you are taking, y r plus sin theta, and from there you are going to give a vote here. Okay. Clear? Oh, what happened? Now example of detecting circles with half. This is that image. You have to partition some images. From there you can get the edge images. Edge images would look like. And then these are the edge images you are getting. You cannot expect perfect circles. From there, you can, So, this is a penny, the penny is like 1 cent, nickel is 5 cents, dime is 10 cent. Okay. So, penny if penny is, if you vote for the penny which is for this one, you are going to get a nice circle here. Again this here, the brightness is, actually this image is very important. Can you see anything else? What? Can you see here something? What? Smaller dot, actually a circle, a very small circle. What is happening? The real thing was small, and but you, the radius of this is known. So, you are just thinking, okay, this is going to give a vote here. The real circle is bigger, and but you assume that your R is small, so you are giving a vote like this, right? These are really the voting space. So, there will be a little bit hole inside. You are not getting only one point, huh? You are doing it with the wrong radius, because you have used the radius of a penny, and these are bigger coins. Okay? So, reverse happen is coming. So, you will see. So, right now you are getting a nice one, and this hole is coming there. And in the other way, right, if you just start with the quarter, you are going to quarter here, quarter here, quarter here, and here you are going to get that same phenomena. Quarter is 25 cents. Okay. Circles are coming from the vote.
No, this in the middle, that smaller circle that we are getting, that is actually the intersection point of all those circles that we are drawing at that
Intersection point of all those. Yes. Yes.
in the other cases, all those intersection points are 1, so we are getting 1.
Yes, for the good cases, they are all putting together. Just think, okay, it is going to give a vote here, right? So, this is maximum. If you reduce it here, what will happen? You will get a boundary. That is what is happening. Okay. So, that gives you some clue, okay, the real circle you are looking for is bigger in size than whatever you are using. So, that gives you the clue. Okay. Now, this is one example, of course, but another example which is probably more important is kind of you can detect an irish, where in a face where is the irish present. So, in our face, the only one thing which is exactly circular for all, which is the irish, right? So, you can do like that. So, again, you cannot just straightforwardly apply this. You need to write your own code. You have that face, and from there you can kind of get the gradient and do the thresholding. You can get this image, an edge image eventually. From there you are getting the half space, looking for a circle of that fixed radius. You are finding two brighter spots there, okay, and then you identify, oh, those two are the irish.
How are we fixing the radius, because everyone's size radius will be different?
Either actually mostly everyone's sizes of the same size. No, see, so that's what, like that's why in that photo, whenever they ask for photo, they ask for a particular shape. They give some format, right? That the face head should not go beyond that, the chin should not come beyond that. Many here it does not, but if you apply for US visa, there the standard is very rigid. It doesn't follow. If that is not matched, they will just on give you visa. Right? So those parts are important, but this is one way of doing it, again very preliminary. So, I am telling that with this, whatever you have learned by this time, using even that you can find some of the important features. Of course, again recording. So, it has been said that the Chinese people, it is very hard. Okay. So, looking upward, looking sideways, looking this. The iris direction method using half transform is evaluation. Okay. So, that is actually basically the code, very important. Line detection and circle detection. Other shapes are not known, of course. Other shapes that we can do will show that parametric shapes. But here, what are the things that for the voting you need to do? Minimize irrelevant tokens first. So, the points that you know are not part of whatever you are looking for, get rid of those. make sure the grid that you are choosing, it is useful for your case. So, too fine or too coarse, you need to make the decision. Okay? Vote for neighbors also smoothing in accumulator array. So, sometimes you give the vote for the neighbors, so that sometimes you get rid of the votes, sometimes you give the votes again based on the requirement. Use direction S to reduce the parameters by 1, and we have seen this for both, for the line detection and for the circle detection, right. For line detection, if you know the R, then only you are looking for only one parameter, the distance. Then what you are looking for? Theta is no, so the distance. For the circle, if you know the theta, know the direction, then only thing you need to find out that A and B on the particular line, not everywhere. Okay. To read back which point is voted for the winning pick, keeps tags on the vote, which is kind of the idea of the dictionary. For each points you are going to store, okay, this point is given vote to this particular cell. Okay. Some pros and cons. A very good thing is all points are processed independently, so the occlusion is not a big problem. What does that mean? Like, that means in your image you have a circle, but only half of the circle has been shown, and then there is a book written or something. Still your algorithm can detect the circle, because these points are going to vote for the circle, so you will find the center. So, occlusion is not a problem. Even if there is occlusion, still you can find the center. Make sense? The line also same thing. If you get a little part of the line, still you can detect the whole line. Okay. Robust to noise. Noise causes problem, but if you do the smoothing, and noise cannot be the majority leader because of the randomness by itself. Clear? What else? Can detect multiple instances of a model in a single pass. Whenever you go through, you just do not go give vote for only one particular line, you can go give vote for all the lines. The same for the circle. In a single pass, you get that one. What are the cons? The complexity increases with the number of parameters. If the radius is unknown, the problem, when actually you will run the code, you will see that if when the radius is unknown, the program will take a long time to run. For other codes, it will be very fast. For running with that unknown radius is going to take you some time, to run, just to run. The algorithm is simple, but the running would be slower. So, complexity of the search line time increases exponentially with the number of model parameters. Non-target shapes can produce points, spurious points. Some other points, those who know that those points on with the part of the real lines, but they are also giving votes. If you are looking for a circle, even all the lines will give vote for the circle. You don't have much control over that, right? So those problems are there, and quantization, like how coarse or fine you want the grid, that also is tricky. It totally depends on your requirement. Clear?
So is this the only algorithm for this? Is this the only algorithm for this detection?
Line detection, there are other algorithms too. Better than this, like the machine learning, other application, if you do that, you are like template matching also can do. Line you have, you are just trying to find that line. Many things you can do. This is a fitting thing. So all you are doing is some fitting. You didn't sleep? Huh? Yesterday? Why? Assignment. Don't know what happened. And there is no one next to him to poke him. Oh, get up, get up. Now only I can see you sleeping. Okay, generalized half transform. Now what if you have to detect some arbitrary shape? Now that is another fun thing. Now you don't know the shape at all. Now you can see, okay, this idea is very, very fun. Intuition is this. Like, for example, you want to find this pattern, a green circle and a little bit deeper green circle in this two particular position from another image. So, reference point is this. So, in this image you want to find this pattern. Okay? How to do that? This is just the intuition, this is not the real thing will come later. So, all you do actually, you can have a reference point, you can find, oh, I have this point, oh, from this point this brighter or darker green is this far away and the lighter one is this far away. Huh? Right. And again do the voting, see how the voting is done. So, you found out, oh, my reference point is here, right. If I have so that means if I get any point like this, all you are going to do, you are going to draw a vector like that. If you get any shape like that, you are going to draw a vector like that and see where they intersect. So, let us do that. So, you got the novel image, the new image, now you are running this algorithm, you found this point for example, okay, and then you found out, okay, this color matches with this color, the displacement vector is this, you just draw that vector here, that point here. Makes sense? The reference point. You are telling, okay, if this point is here, so the this point you are drawing it here. You are just trying to find the reference point. If you find the reference point, you are done. Make sense? From many points, you are looking for only one point. Kind of the idea of the center, this is the circle center, finding the center, right? Same idea here, but this time I do not have any center. All I have a reference point. From this reference point, I know the distance to the key points. So, everyone is going to vote for the reference point, clear? So, this point is giving a vote here, I got this displacement and giving a vote here. For this point, same color, same displacement. So, it is looking for the reference point here, clear? For this point here, this point is lighter color going here, reference point, this vector, it is telling if the reference point is there, it is there. This point, deep color, reference point is outside the space, kind of, clear? The very last one, the reference point is this. Make sense? You put a grid, take the reference point which is getting the maximum vote. Which one is that? The middle one. So, this is the one. So, you just tell, oh, this is the reference point, that means this is the shape that I have found. Good? Clear? Clear? Oh, attendance. Shomadeep, so when you sign today, you just sign the other dates also. It is a new attendance sheet. I just wanted to make it clean, but again I found out one student is there who is not taking the course. Tamajit, okay. Okay. So he'll die. Okay, so this is the algorithm. All the main idea is finding the reference point and kind of getting the displacement vectors. Now, let us see how this algorithm really works. This is for the shape, right? Kind of the shape we took and then from there arbitrary shapes we got. Now those direction could be the gradient direction. So, the example is like that. Gradient direction I am talking about, not a particular shape, but the gradient direction. So, using this you can find any object of any arbitrary shape. This is the intuition, right. Now, I have another objects and you know the gradient direction. So, if you have the edge, you can always find the gradient direction. Yes or no? How to get the gradient direction? Do you know any way of getting the gradient direction? Not perpendicular. Tell me, explain it. What do we need to do? Tell me, that is the answer, yeah. How, what tangent? Tell me the steps. If the next quiz, if I ask, okay, how can you get the gradient direction of a particular point? What is the answer? Huh? Find the gradient first, very obvious. That is the first thing. You cannot just jump into the next thing. Find the gradient first. Probably use the Sobel filter, the x and y direction, find the gradient and then tan inverse, right? So that should be the answer. Right? Isn't it? Get the gradient in x and y and then get the direction, right? So once you get the but this is very important. So once you get the gradient, so for each point you will get some gradient. Each of the s points you got some gradient. Okay, and this is a particular shape, and this is the reference point. A is the reference point in this case. You are looking for this shape here. In a big image, you are just going to look for this image. We are no longer doing a template matching here, but rather half voting style finding. Okay, this is a very interesting way of doing it. Now, all you do actually is you calculate this. For each of these points, you calculate the displacement vector r from the reference point, like this. R, red color is this. Clear? Clear? And now store these vectors indexed by the gradient orientation. So that means for this is the gradient direction and for that this is the vector. So store these two pieces of information kind of in a dictionary which can have for each key value, each direction you can have multiple values. Make sense? This part is clear. For each direction you may have multiple values. The gradient direction could be the same, but the replacement might be different. So if the gradient direction is here, I might have this points also, the theta is like that, but displacement vector is different. Does that make sense? Displacement vector is you have any particular reference point and kind of the vector that the difference between these 2 points is the vector r. That is the displacement vector. Clear? If I, for example, just for simplicity, if I have a particular line here, right, and these are the s points, just think these are the s points, they are having the same gradient or no, different gradient? Same direction or different direction? Same direction, different direction? Gradient direction? Gradient direction, same, right? But I may have a reference point here. Now, for the same gradient, this is the vectors I am going to store. So that means I am creating a table from there. So for this is the information I am storing. For this gradient direction, I have these 4 vectors, whatever. Okay? Clear? So kind of this is the one. This dot means okay. For you may have different. See, this won't be common. This is a unique one. For any point, no other point should have the same displacement vector. The many points can have the same gradient direction, but the displacement vector is unique. Okay? So for each of these, for every point for this gradient direction, you are going to store all the displacement vectors. For this example, in this example, for P1 and P2 2 points, I am storing the gradient displacement. Clear? Should be? Definitely, yes. Based on the reference point, it is different, right? Theta is just the theta and this is the vector. It is magnitude, direction, everything. Okay? Clear, clear, clear? Very good. Now, this multiple, that one thing can have multiple things, this is very important part. So, that's one of the main thing. So, once you get that one, now this is the image, the pattern you are looking for in this image. What you have to do is, for each S point, use its gradient orientation theta to index into the store table. So, for example, in this, for this point the gradient direction is in this way, get the gradient direction, and now for each displacement vector give 1 vote. So, for example, for this point, this point, this point, they are having the same theta. Okay. So, you just apply the same displacement vector for this. Each point actually can vote for multiple if there is multiple things, but right now I am just putting 1. So, I am just giving 1, right. In this way, for each S points gives vote. Gives votes means draw the vectors. Okay. So, you got 3 reference points. So, these 3 points are telling, oh, these are the 3 reference points, this got 1 vote. In this way, the another point, this, they are going to give vote again. Okay. So, you found out that, okay, the particular shape actually is, you can find the objects. So, if you see, okay, this is the wrong point, so the particular pattern can be found here and here, twice.
What is the difference between Hawk transform and template matching?
See, template matching, what is the difference? So, different approach of doing the whole thing.
Why are you doing this? Why are you doing this?
Because it is more generic, you can do of any shape. And see, another thing is, you can sometimes find the whole object out of it. The whole object part is coming next, because it is any arbitrary shapes. And see, and sometimes you
It works, this thing works for different scales also, right?
these things works for different scale. No, reference point is fixed, so no. For scaling, most of the time you will see that what you have to do is, you have to scale the image itself into different things, pyramid style. The way you have seen in project 1, the last plot visualization, the same image has been shown in different scales. That is the usual way of doing it. Many times, whenever you are looking for a pattern, you do not zoom in the pattern, you rather zoom in or zoom out the image itself to find that pattern. Okay? But this idea is clear. But template matching, so here it is totally taking a totally different approach, the directions, and it is like also more robust, because you can use it for anything, absolutely anything. Okay? So, for example, finding a car. Template matching, we have shown that how can you find a car, but there you are taking the whole car. This time we are doing a different thing. I am just finding out the tires. I know that, okay, all the cars should have 2 colors, 2 tires. And I found a central point, kind of whatever point I like, and I found out the displacement vector from that point, right. Last time I have kind of made a dictionary. This is kind of dictionary, right. Key value pair. The key here was the gradient direction, not the gradient direction, and the value was the displacement vector. This time my key is going to be the object itself, the tire, and the value is going to be again the displacement vector. So, in this, for example, this example, for the tire key, what would be the value? Two displacement, very good, 2 displacement vector. So, this. So, for this displacement vector this, for this displacement vector this. The key is same, 2 values. Okay? Because this is the reference point, the same key, the tire is looking like the same. So, key value, the same region for the same direction, I have multiple values, the same region here 2 displacement. One is coming from the, so I found the tire I am storing this. I found another tire, I am storing this. Okay? Yes. For that one key, two values are stored. And now, if someone gives a card like that, now the usual template matching, so let us say, so you found these four cards, the keyword matching, it is kind of the template matching, using that you found the tires, and now you are going to get the gradients. And you found out, okay, this is the reference point, this is the reference point, but nothing here, because there is no car. But if you have bad algorithm, probably you will just tell, oh, there is a car in the middle also. That could, exactly, that could, but that's what you probably would have another features, like not only these two keyword, but that what is that called, that not windshield, that mirror also could be one parameter. The mirror should be in kind of the middle, like kind of always would be in the middle of this thing. This way you can just come up with that. Not only this only one keyword, but with multiple keywords. Okay? So that's it. So what is the summary? Fitting problems requiring finding any supporting evidence for a model even with clutter and missing features can be solved by this algorithm. Fitting problems, these are the fitting problems and the voting approach. Now voting is very important, very strong things. Half transform approaches for lines, circles, any arbitrary shapes defined by a set of boundary points, recognition from the patches, everything you can done with the same algorithm. This is very basic voting algorithm. So that's all for today. So I'll share some content, also read the new textbook I'm suggesting. The textbook is very good to read, very simple, the Davis.